Hello. Hello, this is a demonstration of using approximate distributions. I'm going to use the AQA S4 syllabus June 2014 question 2 as an example. And what we're really looking at here is this connection between binomial, normal and Poisson distributions. And what we've got to do in each of these sort of questions is pick out what the right approximation is. In some ways, this is a bit of a dead art in that with calculators we can work out any of these probabilities directly, but this is how we go about doing it if we only had an approximate available. So let's have a quick look. And as ever, we start with question A. Company manufactures blank compact discs. For the recording industry, quality of these discs is such that 3% have small scratches on the recording side and 25% have small surface scratches on the printing side. So they've given us them some data there. Okay, so have a look at there's two parts to this question, and let's read the first one. A small recording studio orders 200 discs, which may be regarded as a random sample. That's important to us, them saying that, because that means we can now use the stats above from the to do our calculations. From the population of all the discs produced by the company, use an approximate distribution to estimate the probability that more than 4 of these 200 discs will have scratches on the recording side. Okay, so what have they told us? Well, they've told us enough information. I'm just going to move it down a bit here to know that what we're really looking at in A is a binomial, isn't it? It's either scratched or it's not scratched. Okay, so our scratches here, so we've got something that's binomially distributed. Our n value, size of the sample here is 200. And our p probability we saw earlier from the scratches on the recording side was 0.03. So that's our binomial. Okay, so what does that tell us about the mean and standard deviation? Well, here we can see that the mean of the binomial we know is NP, which is 200 is our n times 0.03, which is 6. Now this 0.3 is a very low probability. So if we think about our world, in the world of binomial, if we've got our binomials, we've got a binomial in the world, it can be biased to one side, can't it? A normal is symmetric, and a Poisson tends to be quite biased like that. Yeah, because the probabilities in a binomial in a Poisson tend to be very low, don't they? The probability of something happening in a particular period of time, like a phone call coming in or a breakage or something, is low. So P's tend to be very much less than 1. Here our probability in a normal distribution is 0.5. There's our Poisson, there's our normal, and in a binomial it can be anything, but you don't really, it's not down in this low end, really low end where you've got a p, which is typically around 0.1, is it? You could have a p here of 0.3 or something like that. Yeah, so it's got a bit of bias in it, whereas the normal's nice and symmetric, and the Poisson's really a very low probability over to one side on the whole. So that's what you're picking from, and that's what you're going about. So here in this case, we've got a very low p, haven't we? So what are we going to? We can therefore approximate it. We know that our Poisson is the best approximation. Yeah, approximate with a Poisson. Okay, and what do we have in a Poisson? We only have one parameter in a Poisson, that's lambda. Lambda is the mean, and in the mean, we've already worked that out here. We've got the mean from our binomial mean. So binomial mean, and that mean equals 6. So our lambda is going to be 6, yeah? And what are we going to do here? Well, they've asked us in the question to find the probability that X, the number of scratches, is greater than 4. In our world, I will draw a number line here because just to make us think about it. In this case, we could have had no scratches at the bottom. We're going to have 200 as the maximum, isn't it? And what we've got is 1, 2, 3, 4. So let's do 1, 2, 3, 4, and 5. And what they've asked us is what's the probability that it is greater than 4? Here we are. So that's that area to the right we'd be interested in, wouldn't we? From 5 and more. Well, in our calculators we know we can only get probability of less than or equal to out of them, and so we can find this left hand end is 1 minus, which is probability of less than or equal to 4. We okay with that? So that's how we're going to do the calculation. So let's get our calculator up on the screen, and we're going to go in and we're going to go menu. Let's just hop up one. We're going to go distribution. We're going to choose Poisson, and we're doing PCD, cumulative, because we're interested in less than or equal to. So let's go in there. It's a variable. We're going to put in, what's our X value going to be here? Well, our X value is 4. That's what we're interested in, isn't it? That's the critical value we're interested in. And what's our mean in this case? Well, we've calculated that to be 6. So there's our probability. Press the execute button, and that's going to disappear in a minute when I start writing. So we can see it's 0.285. So that's 1 minus 0.285, which equals 0.715. How about that? So the key bit that led us to use a Poisson there is we had a very low p-value. So we were looking at something that was very low error rate. That's what you see in Poisson distributions. Is something that's a very unlikely occurrence but can happen over a very large number of events, like telephone calls or breakages or little bits of time. So that's our first question, part A. Let's have a look at part B. Let's see what they're doing here. A larger recording studio orders 10,000 discs, which may be regarded again as a random sample from the population. Use an approximate distribution to estimate probability that at most 2,550 of the 10,000 discs will be scratched on the printing side. And remember, they gave us a probability for a scratch on the printing side. That's much higher at 25%. So let's just extend our page and have a look at B. So what have they told us here? They've told us again that we're on a binomial. It's a scratch or a non-scratch. We're starting with a binomial. So let's call that Y, and that's boxed with a binomial. They've got an N, they got 10,000, and they've ordered, and the probability of occurrence is 0.25. So going back to what we were looking at earlier, the sort of 3 types of distribution we've got. Our Poisson was for a very low probability, our normal is for one around 0.5, and our binomials tend to have probabilities around 0.3, something like that. And as long as we've got quite a large number of them, large number of events, so that our mean isn't very, very small, we can therefore approximate from the binomial across to the normal, because they look quite similar there, don't they? They might have a bit of skew on them, but not an enormous amount. So let's start by having a look at the normal then. Yeah, so if we were going to approx with a normal, we've got effectively we need to get into a standard normal. We're going to have to start constructing our standard normal. Yeah. So what do we need in order to construct our standard normal? We need our mean, which in this case mean mu, which can be NP from our binomial again, which is 10,000 times, that's our N, wasn't it? And our P is 0.25. So we've got a mean this time now of 2,500. Yeah, so that's our mean. Now what's the other thing we need to know? We need to know our standard deviation. Yeah, sigma, to put into our normal, and we can get that again from our standard deviation of a binomial. So that's going to be the square root of the variance, and we know the variance from our formulae of a binomial is n times p times q, where q is 1 minus n. Okay, so let's put those numbers in. So we've got the square root of 10,000 times 0.25 times q, which is 1 minus the p, which is 0.75. So that should give us a standard deviation, which is 43.30. Okay, so that's going to be our standard deviation. So that's effectively in scratches, isn't it? So what we're saying here is out of 10,000, we've got a mean of, we expect 2,500 of these to be scratched, and then we've got standard deviation, and the number of them is 40. That's 40 discs. Okay, so we're in the world of normal. We can now convert all our data into standard normal, and because we now need to get our z value, don't we? That's what we need to get into our calculator. And what did they ask us in this case? Let's just stop just a sec, have a quick look back. And they asked us, what's the probability at most 2,500? So what are they interested in? They're interested in us finding the probability that x is at most, so that's less than or equal to 2,550. Yeah. Okay. Now the interesting part here is, of course, that we are converting a binomial, which is actually discrete. Yeah. Like that, and we've already worked out, haven't we, that of the binomial, the mean is 2,500. What they're doing is asking us to find the probability, and that probability on the binomial would be, let's take that one and say that that point there is our 2,550. But actually we're simulating it with a normal distribution. And so what we've got is a problem in that we actually got a discrete step, haven't we, between the 2,550 and the next one up, which would be 2,551. And so what we're going to do to deal with the fact that there's this discrete step between the two, well, we're going to go halfway between the two. We're going to go, right, if our critical value here is going to be halfway between them, because that's the probability we're going to try and calculate in a sec. So our probability of x is less than. So we've actually got to use a value here to put into our formula. When we convert it in the normal, we're going to find the value that, so y is less than 2,550.5 in effect, because we're going halfway between those two. If you think about it, we're doing a rounding type setup, aren't we? In that you've got to go up or down in the middle, and you'd rather round down to 2,550 or round up to 2,551. So there's our probability, and we've got to convert that into a z value. So what's our z value here? Well, we know we're above there. We've got a positive one because we've got 2,550.5. That's our actual value that we're interested in here. We're going to find the distance from the mean, and we're going to find that distance in terms of standard deviations. So there's our calculation, and that figure is, I'm getting our calculator, so that equals 1.166. So there's our z value for our calculation, and as ever, and that's why it's all a bit weird really, because we're going to stick it in our calculator now, aren't we? And we're going to find out what's the probability. We're going to find the probability that Z is less than or equal to 1.166, and we're going to use our standard normal. So let's hop back to our calculator, and we're going to go distributions, normal. We're interested in NCD. Our low value, we want just a very large negative number because we're starting at the bottom, so we'll start without many standard deviations away. Our upper value is 1.166. Because we're doing our standard normal here, we've already worked out our Z value, so we're going to put sigma equals 1 and our mean is going to be 0, because that's our standard normal. So we just put that in the calculator, push the button, and we're going to get 0.878 is going to be our P value. We can check there that our Z low and our Z high figures, lower and upper, are as we would expect in our calculator. So here we've got 0.878. So that's pretty straightforward. And that answers the question, and for that one I think we get 6 marks for doing that bit. Just out of interest, as we've got these lovely calculators, let's have a look and see what the actual figure would have been as opposed to the approximation. Distribution, binomial, BCD, we're interested in there. And if we put the figures in, so our X value, they asked us 2550, number of trials 10,000, our P was 0.25, we would have got the answer 0.878. So we could have got that pretty quickly going the direct route. In some ways, the sort of historic way of doing business is a bit redundant with these wonderful calculators that we have. You could do exactly the same thing if you wanted to with the original binomial. And if we went back and did the first part, part A, we were looking at x is less than or equal to 4, so it was greater than 4, therefore we calculated x is less than or equal to 4. We had 200 tiles, we had a probability of 0.03, so we got the binomial would be 0.28097, 0.281, which of course is pretty well what we got in the first part anyway. So I think what we're really down to here is principles of when it's right to apply it and not. Okay, here's one of my little quick summaries for this topic. So if we're starting with a binomial and we've got extremely high or extremely low values of P, less than 0.1 or greater than 0.9, we're going to use our Poisson. And in that case, we're going to get our BNP, and we're going to convert that into a Poisson by finding our lambda, which is going to be n times P. If we've got, secondly, if we've got a P value that's not as extreme, somewhere between 0.1 and 0.9, and we can check that our NP is greater than 10, so it's not extreme, and it's not extreme at the other end either, we need to check both ends, that our N1 minus P is greater than 10, then we should use our normal. And we're going to convert that again, because we're going to start with our BNP figures that we found, and we're going to turn it to a normal where the mean is NP, and the variance here, because remember we put sigma squared, and we write sigma squared here, so it's going to be our variance there, is going to be NPQ, and we can calculate those pretty quickly from the data that they give us. And that gives us the best approximations. I'm sure there are better videos explaining all the detail and doing some demos. Mr. Nickel TV's got some quite good stuff on that, but here's a very quick way of running your way through it. So look for extreme. If it's extreme, it's Poisson. If it's near the middle, it's more normal. Aha, normal. Use the normal. Have fun. Best of luck.